So as far as Nvidia, I think you all associate us with computer graphics. We invented the GPU, or graphics processing unit. Basically, these are among the largest chips that are done in the industry, and we're always really pushing the limits of performance and power and area. So accordingly, from our EDA tools, we need very high capacity, very good performance, and very good accuracy. So we take chips like Volta and we apply it to a number of different markets. In the upper left, of course, graphics is our bread and butter, and we've started doing ray tracing in hardware, which is sort of the holy grail of computer graphics. But the architecture of a GPU is also applicable to several other large and fast-growing industries, such as supercomputing, deep learning for artificial intelligence, and in the future for really driving autonomous vehicles as well. So we're getting traction in all of these markets. This is sort of a schematic representation of the chip design cycle, and talking about when we use various static sign-off tools. And the idea is that we're using different combinations of the tools in different phases of the design process. So, you know, when you're starting with an RTL module creation, maybe what you can do at that point is you can run lint. And as the chip comes together and is more functionally complete, the block is functionally complete, you can start to run CDC and RDC. And then as the different blocks are assembled, you can run multi-clock CDC and RDC. And finally, before tape-out, you want to run a gate-level check as well. And so, yeah, as you can see, we're applying static sign-off tools continuously throughout the design cycle. So why do we do this? So lint is great for an early vetting of the RTL. It's quicker and easier to get feedback than running simulation or synthesis. And CDC is it's a formal tool giving us complete coverage to ensure that our interfaces are clean. We really try to minimize the potential for CDC problems by having strong design guidelines, using golden IP and certain simulation techniques, but still, those, as Prakash mentioned, those techniques do not cover everything, and we need a formal solution to cover everything. And RDC is kind of a similar situation where this is a class of bugs that can be quite subtle and quite hard to find, and if it escapes into silicon, it can be really hard to debug. So again, RDC tools provide a formal solution to catching any problems with your reset synchronization. Just a few examples of types of problems that these tools can find. On the lint side, it's anything from very simple things to looking at more corner cases of your case statement usage or arithmetic widths, or even more subtle problems that might even be missed by simulation, such as self-determined expressions, where unless you had the right test case in simulation, you might miss it, and yet a lint tool can flag that. On the CDC side, I mentioned it can formally verify all of the interfaces, clock domain crossing interfaces in your design. And by running it after assembly, after all the blocks are put together, you can catch things that may have been done post-synthesis. Perhaps in this example, we've inserted pipelining registers in our design, and perhaps that was done by an in-house tool. And we want to make sure that those registers are clocked correctly. So the CDC would catch that at that point. And finally, why do you run it at gate level? Well, again, things happen during the design closure process. There may be more DFT logic going in. There's ECOs that are changing timing or function. And so a final check is done at gate level before sign-off. So to apply these tools, some of the best practices that we recommend, much as Hamid mentioned, there's a lot of emphasis on automation. We want to make it very easy for our designers to run this in sort of a push-button manner, and we want the grading of the results to be clearly go or no-go, and we post it to a dashboard so that the chip management and the design teams can see whether they're clean as far as static sign-off. So all of this is very automated and run frequently. And what static sign-off is not is somebody just sort of running CDC one time and saying it's okay and telling their manager. It needs to be repeated and continuous so that you know that no bugs are slipping in. And our automation provides that capability. Another question is, when should you run static sign-off? Should you run it at the beginning? Should you run it at the end? The graph on the right, I tried to illustrate that the completeness of the design is continually increasing over the design cycle, so that all of the RTL is there, all of the RTL is correct, your constraints become correct over time. So you get the most complete analysis by waiting, but on the other hand, there's an exponential increase in the cost to fix problems the longer you wait. So there's no one answer. You really need to be running both early and late. You want to catch the low-hanging fruit at the beginning of the design cycle, but then continuously run static sign-off so that as things come together and are more accurate, you're seeing any new problems that emerge. If you're evaluating new tools, these are some of the things that differentiate static sign-off or really any EDA tool. Of course, the main thing you're looking for is the coverage and the correctness of the analysis. That's why the tool exists. And you want to make sure that it's catching everything that you're concerned about and that it's not an optimistic tool. It's conservative and it's got to flag everything. Now, static sign-off tools are notorious for being noisy. They'll generate lots and lots of messages that are either incorrect or not of interest to the designer. So this is another area where tools differentiate from one another. You want a tool that doesn't generate a lot of false violations. You want a tool that generates compact reports. And ideally, you want a tool that focuses on the root cause of the problem rather than all of the myriad symptoms that are triggered by that root cause. So that's something to look at when you're comparing tools. And finally, because of the emphasis that I think we all have on automation, the tool really needs to lend itself to automation, scriptability, and debuggability. So, for example, the implementation tools like synthesis and static timing analysis are really good in this respect, right? They all have TICL interfaces, they have access to design objects, they have attributes you can query. We need the same things from static sign-off tools so that we can script things and have them be push button. So I hope you're getting the message that static sign-off is really something that is essential. It can find problems earlier than other tools. It can find some problems that other tools may miss altogether. But to do that, you need a highly accurate tool with high performance and just a high-quality analysis. That's what you need to find. And if you find that and put it in your flow, you're going to have a smoother path to design convergence, and you'll have much less risk of having bugs in your silicon that you tape out. Okay? So thanks for your attention.
From your experience, why would you use multimode CDC over single-mode CDC?
I think the analogy is very similar to for your static timing analysis tools, where you count on them to be able to do at least multi-clock analysis and multi-mode analysis as well. And early on, maybe you have sort of a simplistic high-level analysis where you can define the one clock and then run single clock CDC. But later, as you get further along and are getting closer to sign-off, you want to use like your real STCs, your real timing constraints. Then they have multiple clocks, so you want a tool that can support those STCs and do the correct analysis. I think it's also interesting. People are very tempted to do that analysis with STA, and it's sort of easier to pick out the critical clock combination for STA, but what's critical for STA is not necessarily critical for CDC. So, you have to be really careful, or probably you shouldn't make assumptions like that for CDC.